So, welcome, CS109 on today's Thursday, right? Yeah, Thursday. First, announcements as always. We have changed the due date for homework 4, so everybody has a bit more time. The reason is that there seems to have been a typo in one of the questions, which basically made it nonsense. So if you were really, really stuck, I think I heard that also Piazza, there was a lot of questioning and answering. And Raphael tried his best to clarify all the points. So I think, especially for this homework, Piazza was probably a really valuable resource to look into there. Yes, question? What? Which question had the typo? Okay, so there's a post on it. And have you sent the email already? There was an email, I think, from Piazza with this announcement thing, right? So we can send emails from Piazza that circumvent all your settings. So even if you say, please, Piazza, never, ever send me an email, if we hit that button, everybody should still get that email. So that should contain the clarification and the change of the due date. Is the homework file itself updated? Yes. Yes. It was up, it didn't just happen. It's been a while. Oh, it happened a while ago. The decision was just that because of that, we want to give you an extension. That also means that for this homework, you won't use late days because we already extended the deadline beyond everything you could have had achieved with late days. So for this time, there's only one Dropbox, and this one Dropbox is going to close Monday midnight. Oh, my second announcement is missing. That's odd. I apologize, then I need to dig that up later again, or I need to do it half out of my memory. So one of you guys emailed me with this cool information that the data science visualization guy from the New York Times is speaking tomorrow in the IACS seminar. That is, lunch is at 12:30. The actual seminar starts at 1 p.m. Opposite the street in Maxwell-Dworkin. I think it's G115. And I forgot his name. I'm sorry. I should have had an announcement there. I know I wrote it. I know where it is. No. Oh, how did that happen? Okay. Thanks. So Chris Wiggins is going to talk tomorrow in the IACS seminar. So there are, yeah, I think everything else I said is correct. So I heard that this is going to be really interesting, and I think Raphael has also shown some really cool visualizations from the New York Times. So this might be worth attending if you're interested in learning more what is happening at the New York Times. So just a short recap, because we're going to talk a bit more about the support vector machines today again. So we said we have a data point. We have our data points, X, and labels. And for the support vector machines, the labels were not anymore 1 and 0, but -1 and 0. 1 and -1. And we said that we have the separating hyperplane, and we have this weight vector W that gives us the orientation of our separating hyperplane and the bias that we can use to shift the hyperplane around in the space. And then we just look, when we want to predict a new data point, we just look at which side of the plane this new data point is, and according to the side, we predict the class. We said support vector machines use maximum margin classification. So the goal is to make this area as wide as possible, and the data points that are closest and basically define this maximum margin are the support vectors. So, and just because this is really important, I wanted to mention this again. When you use a support vector machine, you need to take care about normalizing your data. Like if you have an extreme difference in variance and the different features you have describing your data points, you're going to run into trouble. So there are different ways to normalize your data. I think mean zero and standard deviation of 1 is about the most popular out there. And again, also it's important that you normalize the test set in the same way. So you estimate your mean from your training data, and that mean vector you also use to normalize your test data. Do not re-estimate the mean on the test data. And then we had this idea of a kernel function, right, that can give me similarity between points in a higher dimensional space without actually having to compute the representation of these points in this higher dimensional space. And the reason for this was that in a higher dimensional space, I can achieve linear separability of my classes, even though they were not separable in the original space. Okay. And then last time we didn't have time anymore, but I wanted to show you this. So you've seen this applet before where I showed you the influence of C, right? What was the parameter C for here? Do you remember? The slack variables, exactly. That is the weight on the slack variables. Slack variables were the misclassifications, right? Where I had points on the wrong side of the hyperplane. And I allowed this, but I penalized for the distance on the wrong side. And C, you can tune how much you penalize for these errors. And now I'm going to show you the influence of the kernel itself. We're going to do an RBF kernel. So I can actually do this circle shape here. And if I just say start, this gives me a reasonable classification boundary here. And what you can see, because I'm using this RBF kernel, I can get this round decision boundary, although the support vector machine itself, right, this weight vector only has the separating hyperplane, so it's linear. But it's linear in this higher dimensional space, and if I project this down, I can get complicated decision lines. And they actually can get more complicated than this. So if I put some additional data points here, maybe, and let's make some challenges here. So you see this had an influence that I just put this additional data point here. And in addition to my C, I have this beta parameter here. In this applet, they called it beta. In most implementations I've seen out there, this is called gamma. Gamma is just a parameter that you can use to tune your radial basis function kernel. What you can think of it as increasing the dimension that you cast your points up to in a way. So if I make this larger, my decision boundary changes, and you see it gets a lot more freedom to move around, right? And you see already something happening here. What's happening here? Yeah. So we're starting, I think, to overfit, because it's like here going all the way out just to account for this one data point. And you can see all these little insulas here starting to form. And on the other side, if I make this guy too small, then you lose your flexibility and you get a more regularized decision boundary. Like this trade-off of something where you can increase the flexibility in your classifier, right? We've seen with every classifier we had so far. And this notion of overfitting is always going to be there. And with support vector machines, you need to especially care about it because you have so many parameters that you can tune. Like with every classifier before we had like k nearest neighbors, there was basically just the k to worry about. With the random forest, you had maybe the number of variables you used to split and the number of decision trees. With the support vector machine, you have all these additional things like which kernel to use in the first place, which parameter to choose for that kernel, how big what the value for C should be, right, to penalize your slack variables. And all of this you need to tune. So C, I already asked, so this is the weight for the slack parameters, and these are the things you need to care about when you tune your support vector machine. And we said if I want to tune my parameters in a way that I take the best in the end, we're using cross-validation, right? So again, this notion, you have your training set to fit the support vector machine, then you have the validation set, where you basically look what is the performance at the moment with this setting of parameters, right? And then once you tune that, you can compute an actual test score to see how well your optimal parameter setting from the validations runs before perform. And there's one thing to take into account here. Normally this is done with a grid search. So what that means is it's going to get very, very computationally expensive. Because what you basically have to do is, this is just two parameters here. I assume this is the cost of the slack variables, and gamma here is for your radial basis function. And this is a heat map. So remember, Mark, I think, said don't use rainbow colors. But I stole this from a publication because I wanted to have actual data in here. And they used this rainbow heat map. So what you see here is I have points here for every combination of gamma and C, right? They didn't just fix, for example, the cost here and then try different gamma values, then went for the best range there and then tried to tune gamma, because they would have ended up somewhere here, right? So if you do not try every possible combination, you can still find a minimum, but it's going to be a local minimum. You don't know whether that is actually going to give you a prediction performance that is somehow comparable to the actual more global minimum. So what you typically do in such a grid search is you literally take every possible combination of your parameters and compute cross-validation with those. And you can think this is just something that looks so easy with scikit-learn, right? You just have your dictionary where you say, I want these 5 parameters to be tuned, and this is the range, right? And then you just call the cross-validation function, the grid search function, and then you wait for hours, and you wonder why. And the reason is this grows exponentially with every parameter that you put in there. And you have to test every combination. This is what the grid search does. Right? So it's worthwhile to think before, what is an actual range that makes sense here? Maybe do a few tests beforehand about the range that you want to test. Okay, any questions to this grid search things when I have more than one parameter to tune? Yeah? It's very expensive, that's true. I don't know if you can optimize. You can use real optimization. One very cool approach I thought is actually coming here from Ryan Adams' group, from Jasper Snök. What he did is he uses a Gaussian process that optimizes the parameters for you. So what this does is it would start kind of with random positions in here, right? And then from there, it would basically say, it would assume a certain amount of smoothness within this parameter search space and would basically say, because you have an adaptive step width if you want. Like if I'm up here, can you see my pointer? Here. If I'm up here and I tested a point, maybe that is so low, right? And the Gaussian process also gives you the standard deviation here that is assumed. And maybe you then already see there is no gain whatsoever in testing the point right next to it. So you would skip this whole area, whereas when you get into this area here, you would maybe go with a finer step size to actually look for good parameter combinations. So another thing is, especially in the context of deep learning methods most of the time have so many parameters to tune that, what's his name? So one of the profs on my floor always jokes and says it's grad student descent, because you basically need a whole graduate student to tune all the parameters, and they find a setting that works well, and then the next grad student starts with that parameter setting and tries to find an even better one. Like, this is how complicated it can get to tune those parameters. So, and there's even been papers that say even if you just do random search, because it's not feasible anymore to do a grid search. So even if you just randomly pick points, you can still sometimes do better than an expert who's trying to set those by hand. So it's always worthwhile to try to tune parameters with your data, not just with manually tuning knobs. Grid search is the simplest one. For something like a support vector machine, I think grid search is still good enough. If you run into more complicated methods and models, there are other things you can use to tune the parameters. Different questions? Okay, then with support vector machines, we actually briefly need to talk about multi-class classification. With everything we had before, this came kind of built in, right? With the k-nearest neighbors classifier, it didn't really care about how many classes there are. You only had to tune k. Also with the decision tree, you were just looking what is the majority class on the leaves. So the model itself didn't need to know anything about how many classes there are in our data set with respect to tuning the training method. Now, support vector machine is just one separating hyperplane. So I can just distinguish one side of that hyperplane or the other side. So I only can solve binary classification tasks. But the classifier itself performs so well that people also wanted to use it in a multi-class setting. So we need to address this problem somehow. And there are two ways. Can you maybe already think about them? There are two things people do. What? Yes, build a hyperplane for each pair separately. That is one. Yeah? Two hyperplanes. For what? Oh, so because then you can get more sophisticated decision boundaries. So on the long side, like within boosting, where you have this decision stamps, and by combining them, you got a more complicated decision boundary. You get the complicated decision boundary in a support vector machine by using the kernel, right? And then you project it down. So you're already fairly flexible. You just still only have this binary classification with respect to what is on one side and what is on the other. Yeah, so this is actually the one missing is the first one I have in my slides. It's called one versus all. This is what people normally do, because then you have to train n classifiers if you have n classes, and you take the classification with the greatest margin. Do I have this in here? So this is what I do. I just pick the blue class first, and then with these two guys, I merge them into one. So I do not distinguish anymore between yellow and red. I just give them the same label and train this class against the rest. And then I do the same for the yellow guys. I train this class against the rest and this class against the rest. For each of the classes, I have to train one separate support vector machine. And then the other solution that we had here is 1 versus 1. And you have n times n minus 1 classifiers, right? You have n classes, and then you train one against all the others, divided by 2, and you just take the majority vote then. Oh, I actually didn't say that here. Greatest margin. So when I now have a new data point, and it's somewhere here, how does that actually work? I look which one is furthest away from all of these decision planes. So if it's here, okay, I'm stuck. Does somebody see it? How would you classify a new data point here? So this is one versus all. So I classify this guy with respect to this. It's here. It's here. I just don't see the greatest margin at the moment. I'm sorry, I'm stuck. I'm going to deliver that later. So with 1 versus 1, it's just the majority vote again. So that's easier. So you have all these classifiers, and you trained looking just blue against yellow, and you actually don't care about red. You just delete those points, basically for that classifier. And then you do red versus yellow, and blue versus red. And then with the new data point, you just look what are the different classes that are predicted by all of those hyperplanes, and you take the majority vote. So, and I found this on the Scikit-learn webpage. I believe it's also been linked on Piazza. I'm not entirely sure. I think one of the students did that. I just wanted to show this because I think this roadmap is kind of cool. So you start here, and then it says, so you have a data classification or exploration problem. What do you do? And the first step is you look whether you have more than 50 samples. And if it's a no, then it says, please go and gather more data. And I thought that's kind of a funny arbitrary threshold, right? But this was probably true that with 50 data points, you can't really do much. Although with the iris data set, we've already seen there was 150 data points, right? It's not that much more. So, but interesting here, I thought for your final project is that you at least like get a feeling for where you end up with respect to these 4 areas. Especially, you want to predict a category, right? And if yes, then you have labeled data, and then you're in the area of classification. If you want to predict a category and you don't have labeled data, then you're in the area of clustering. We're going to talk about clustering today. And if you instead want to predict a quantity, then you're in the area here of regression. If you have labeled, right, which is a score in the case of regression. Or if not, then you're somewhere here in the dimensionality reduction area because you want to explore your data further, maybe. So I think just for you to know, I think this is worthwhile to look at and also get an overview what different classifiers maybe are out there. Like for your final project, you don't have to necessarily restrict yourself to the classifiers we talked about in class. If you know that something is out there and you already have a feeling that this is going to work much better, maybe you've used it in the past or from other courses, or you just read a paper about it and want to try it, like you can look at the other scikit-learn classifiers as well. They're going to work, like programming-wise, it's always just the fit and predict, right? You just need to know a bit more about the internals to know which classifier to use. And this brings me to my discussion question. So I thought this map was kind of cool, but what it was lacking was the internals here for me. So it has this, have you more or less than 100K examples? And then yes, maybe go this route, or no, go this route. And this says even try this. And if it's not working and you have text data, then try this, or otherwise try this. I just wanted to have a simpler map of the classifiers we talked about so much so far in class, and except for this guy, which we're going to talk about later. So I would like you to take 5 minutes, talk with your neighbors, and think about how you would arrange these classifiers. So I'm going to start because we haven't really talked about deep networks yet, not at all. So this is not super clear math science, right? There are, I didn't say whether this is log scale or something. I just want you to develop a feeling or think about which of these classifiers would work for a lot of samples or with only a few sample points, with a lot of features in a very high dimensional space, right, where you measured a lot, or with very small feature sets. I'm going to start and just show you what I mean with this deep network. So deep networks typically extract the features kind of themselves, and they go kind of crazy with that. So I have a large number of features that they work with, and because of that, I need an insane amount of samples to actually train this. So I would take the deep network and put it up to the upper right corner. So I'm going to give you 5 minutes, and I want you to think about where you would put the remaining classifiers just with respect to each other, with relation here. Think about quadrants, like would it more be lower left or lower right corner? Like where would you put those? Okay. 5 minutes are up. Have you kind of reached consensus, at least with your neighbors? Let's try. So I'm actually starting with something that was kind of ambiguous for me. So I'm not claiming that we're going to come up with the ordering of these classifiers, right? I just think it's a very nice way to think and get an overview of the different strengths and weaknesses of the different methods. So let's just start with the decision tree. Where have you put the decision tree? Yes? Like there? Not that many samples, but you need, no. What did you say? More features. And less samples. So just as a general thing, if you go up in the number of features in nearly all classifiers out there, you also want to go up in the number of samples. Just because your space, because of the curse of dimensionality, kind of gets large, if you want to think about it that way. So you need more points to fill it. But this, yeah, this could work. I personally put it actually further down here. So the decision tree, in my 5 minutes that I thought about it, I put it very much down, not because it wouldn't work in the other scenarios, but because of this white box, right? So the decision tree, I personally would only use if I'm interested in looking at the actual rules that it built. Like I want to know why it classified the disease that way or something. Maybe I'm going to learn something, gain insight into the biological system. And if you have a lot of features, this gets complicated very fast. Like the trees get insanely large. If you have enough samples, even if you have not so many features, but your problem is kind of hard and you have a lot of samples, what happens is you split with the same features over and over again, but your tree gets very deep. And then I think you can also not interpret it anymore very well. So this is why I personally just put this here. But with respect to performance, yes, could go further up, be more in this area here. Okay, and then maybe in comparison to that, where would you put the k nearest neighbors? So first of all, sorry. Did anybody put the decision trees like widely different? There is no real right or wrong here. This is just my opinion and other people's opinion. Yeah?
I felt like you needed more features so that you have more meaningful branches. Like if you only have 2 features, I don't know, which is why I had it higher.
Okay, yeah, so this didn't necessarily mean for me too. This just meant few. So yeah, of course, we can put it higher up there. That's true. If you only have 2 features, those rules most probably aren't that interesting, right? So k nearest neighbors. Where? Yes? Large number of samples, low number of features. Will we put it all the way up here? Why am I hesitant to put it too much to the right side, the k nearest neighbors? Yes, computational intensity, right? K nearest neighbors has, for every prediction it does, it has to search through the entire data set to see which points are near. So if you have a ton of samples, right? We're talking maybe gigabytes or terabytes here. There are still people who do this. There are NVIDIA conferences and CUDA and other GPU programming conferences, and k nearest neighbors is still a topic there. Like it's not that this classifier has been developed in the past and nobody's using it because it's actually working quite well. People try to address this computational challenge. But if we're talking scikit-learn implementation, most probably it's not the fastest out there. So I would put this guy a bit more here, like a bit more cautious with the number of samples I'm using, and then maybe like here. So support vector machine. Yeah. A lot of features and a lot of samples. Yeah. So like there. Somebody else having it there? Yeah? Yeah. There are two things here. You can do this, right? There are also techniques to speed up the computation here. Personally, I would, number of features, absolutely right. This is where support vector machines shine. The big thrill even about support vector machines is they can still work if the number of features is greater than the number of samples. Like normally, if somebody comes and says, I have more features than samples, nearly every machine learning person said, go home, right? Or give me at least just a subset of those. That works well. Support vector machines, due to this large margin, are kind of robust against this. Of course, there are limits to the robustness, but it can work in these spaces. The reason I'm not putting it totally to the right is not only that it can shine in this area, it's also finding those support vectors. Again, you need to go through all the data, right? And it's a quadratic programming problem, so that takes time in the optimization. So normally you want support vector machines if you have high dimensional data, like a lot of features, and you don't have that many samples. This is where they really shine. That doesn't mean you can't use them there. And then our random forest. Yeah? Above and to the right of decision trees, like there. There, further down. Maybe kind of at k-nearest neighbors? Not sure. Yeah, I'm not sure either, right? This is just about, I wanted to discuss with you the different strengths and like how they relate to each other. I'm not set on this being the ultimate solution in which classifier you should use. I just think this is a nice way of comparing them. So yes, it's somewhere around in this area, I would say. You can, so the single trees normally train very fast, and the predictions you can make in parallel for all the trees. So you could use it with larger sample sizes than a support vector machine, maybe with respect to computational complexity, but you don't want to go too crazy with the number of features with respect to the number of samples. So I would kind of stay in this diagonal thing, maybe. Yeah. Yeah, I think that is kind of the picture. Cool. So any other questions to the supervised learning part? Because we're going to do unsupervised learning now. Dive into the new topic. Okay, cool. So no labels anymore. Nobody telling us this is class A, this is class B, this is an apple, this is an orange. This is unsupervised learning. There are, in my experience, two scenarios where you're using unsupervised learning. One is getting labels is so expensive and cumbersome that you don't want to do it, right? So there's been work, for example, in image segmentation using clustering methods. And this doesn't have to be, right? I can give a digital pen, even a Wacom tablet, to a lot of students out there and have them segment images. So I can totally get the labels for those images. And if I look at a segmentation of an image, I can say this is correct or not. So I have a notion of the labels actually in my mind. But sitting down and labeling images is time-consuming and kind of boring. so people don't like to do it. So they were hoping that they can come up with unsupervised methods and spare this annotation part. So this is one scenario. You actually have labels on your data. You already know which labels you want, maybe even. You know how many classes you have, for example, and you just don't want want to spend the time and effort to generate those labels. And then there's the other scenario where you're really exploring, and you actually don't really know what you're looking for, and you're just hoping to find patterns in the data that you want to interpret later. So these are the two scenarios I came across with. So we're going to talk about these three methods. K-means, very popular. Hierarchical clustering, we've seen in one of the final projects, the one with the presidents, where they said our presidents cluster in three categories, and they had this dendrogram. We're going to see this again. That was hierarchical clustering. And then there's mean shift clustering. And we're going to talk also a bit about how you could try and evaluate the performance of a clustering. So we're in the unsupervised setting now. So as I said, no labels, right? This is what my scatter plot looks like. Everything is one color now. But still, I can see patterns, right? If I look at the scatter plot, I would say, two classes here. So in the k-means algorithm is not related to k nearest neighbors. It's just that it also has this k in it. So k here is the number of clusters, and you need to know the number of clusters in advance. So in this case here, we're going to set k2. But this is a parameter that you need to give the algorithm before it even starts. So you choose the k random positions, literally just 2 random points in your feature space, and then you assign those cluster centers to these positions. What does that look like? I have my space here, and I just randomly drop 2 points. And what you do now is you compute the distances of every data point to these 2 points that I just dropped. These points are my potential centers of the clusters. So where I want to end up with is having one center inside of this cluster in the middle and the other one here. If this would be apples and this would be oranges, right? I basically want my cluster centers to represent the ultimate apple, like the example of an apple and the example of an orange. And then later on, when you want to classify or have new points that you want to assign to the different clusters, you see, you look up which one is nearer, right? Is this new data point nearer to the optimal apple or to the optimal orange? This is the way to think about this clustering and this these centers. So you compute the distances of all the training points to those centers that we have at the moment, and you assign the points to the nearest cluster center, and then you update the center. So it's an iterative method that tries to move these 2 center points now in a way that they wiggle inside these clusters, one iteration after the other. So this is how this works. You have your 2 points. And now I said for each of those green dots, for each of my sample points, I see what is the distance to the red guy and to the blue guy. And I assign the point to this center, which is nearer. So this is what I get. All these points are closer to the red center point, and all these points are closer to the blue center point. So now I have a clustering, right? It's not a good clustering, but it's a clustering. And in the next iteration, I now move these points to the center of the cluster I found. So I'm basically saying, this is my clustering now. Now give me the center of this cluster here. And then I move the points to these centers. And then I do the same again. Now I have new centers here. I can, again, go over all the data points, see which center they're closest to now, and assign the colors again. And this is what I get. This already doesn't look that bad anymore, right? So this is the way it iteratively optimizes finding the centers of those clusters. You can see within the next iteration, I'm actually pretty good. And so you converge when you don't have an update anymore at some point. Yeah? This is K, exactly. So the question was, how do I decide how many centers to have? This is K. This is a parameter you need to give the algorithm in the beginning, unfortunately. So you basically need to know for how many clusters you're looking to find them. So this is an example here with a bit of more data and a bit of more clusters. And what you can see here also is the points moving in and being slowly attracted to the different centers here. Can I go back? Yeah. So this is another example from the image processing domain. This is just an example image, a color image. And this is now different to the digits data you've seen before. With the digits data, we said each little image patch was one sample, right? And each point had then, each pixel in that image patch was one feature dimension. So a sample point would be one patch, and each of its columns that described it would be one of the pixels in the patch. Now here I did something different. I say each pixel in this image is one of my data points, and each pixel is described by its three features, which is the R, G, and B, red, green, and blue channel. So I have as many data points as I have pixels in this image, and each point is in a three-dimensional space. It's just a different way to look here. You can see this is the red channel, the green channel, and the blue channel of this image. So blue, for example, you can see is almost only in the sieve. And then red, this guy is very red, so it's very bright in this red channel image. This is the way to read these type of images. And now I'm going to cluster those points. And what you're going to see is if I only set K2, I get these two clusters. And this is, so the mean of the cluster now corresponds to a color. Right? Can you see here? If this would have been three-dimensional, right? Each point here is one pixel in my image. Right? And this would be red, green, and then I have another dimension for the blue here. So I can represent the actual mean of that cluster, the center, as a color. So what I did here is I took the image, I clustered all the different color data points, and the two centers, one was a kind of orange, and one was this green-bluish color. And then I assigned each pixel to the cluster it comes from. You can see I get a binary segmentation of the image, where I have this green bell pepper merged with the sieve, and I have the red yellowish bell peppers merged with the table. So if I set K equals 3, I get 3 clusters, so I have an additional color here. The others converged kind of to the same colors. And this time I can actually segment out this blue sieve. And this is what I meant. This is an example if I would be interested in the different objects here in the image. I would kind of get this blue sieve out here without having to sit down and actually produce a manual label. Of course, if I would have done that, each classifier out there most probably would have done very well, right? Because the blue really separates out here. This is also the reason the clustering can find it that easily. So now if I increase the number of clusters, you see here I get finer and finer segmentations of the bell peppers. And I also get my colors back, of course, because I'm increasing K here. And I think I go until K equals 10. And another observation here is the K value for these two clusterings is the same. They both have, I think, 10 colors. But they look very different, right? So like this bell pepper here up here is orange here, and it's lighter here. And instead, this clustering here spent one cluster for this dark area on this green bell pepper, where here this is just one shade. And this is something very important to consider when you use k-means clustering. because of this iterative process, and the result you get actually depends on the random initialization at the beginning. So if you run this multiple times, you're not guaranteed to end up with the same solution each time. It's not deterministic. So the good news is it's always going to converge, right? You're not going to sit in front of your computer and wait until you run out of iterations. At some point, you're going to get your K clusters. But the result depends on this initialization, and the number of clusters you give it is important. It can be sensitive to outliers simply because we computed the average, right? The new center is updated by the average distance to all the data points that were assigned to this cluster. And a mean is always sensitive to outliers. What you can do to make this more robust is to take the median and actually end up on one of those data points. And then people have tried also different initialization methods. So you can choose these random positions, as I've done in the example. You can also just say you choose one of the data points as initial center. That makes sense because if your space is kind of large, right? If I just take, and my data is kind of in the middle, if I just take a random position, I might end up way, way out there. Which doesn't matter that much after the first iteration, I'm going to be close. But you can also just say, okay, I'm going to choose data points right from the beginning, right? Then I'm already in the area where I want to be, and you just iterate and try to find your centers. Yeah, you can even start and not put centers, not start with assigning centers, but to random cluster assignments to the data points. So I just take my green points, and I just randomly say red and blue, red and blue, red and blue. And that gives me 2 clusters, right, that I compute the center of, and then I can go from there. And you can start several times, and you're going to see that some clustering seem to be more stable. Like, you more often get the result. Like, you start k-means 10 times, 20 times, 30 times. And out of those 30 times, 20 times, you got the same solution. Then you maybe want to trust that solution more, right? You have 30 random initializations, and 20 of those converge to the same solution. So you can kind of have a sense that this might be a more stable clustering than the other solution. So what if you don't know how many clusters you're looking for? This is not as easy in unsupervised learning. I say here you can do cross-validation, but you have to think about it a bit more, because for cross-validation, we needed some type of score. And it's not immediately obvious how to get a score for clustering if you don't have labels. Nobody says this was correctly assigned to this cluster. So but what you can do is you can partition the data into n folds, as we had it before, and you cluster on your training data, also as before. And instead of having a misclassification rate, right, this accuracy or precision recall, what you can do is you can compute the distances of your test set to the new centers you found. The idea behind this is if it's a good clustering, then it's also going to be, for the training data, then it's also going to be a good clustering for the test data. And a good clustering means that those centers have the points they belong to. Like if I have the center of a cluster, then the new points are going to be near that center again. Okay, that's all I have to k-means. So the most important points are you have to put in k and you have to run it multiple times. Yes?
So you compute the distance to the nearest center?
Yeah. Because otherwise you don't know where it belongs, right? Normally you would maybe want to, if you have someone who's willing to just maybe provide you with a few labels, then it's very cool and you can use those, right, to compute an error, because then you know which cluster they belong to. But if you just have the unlabeled data, then you just can choose the nearest center to compute the distance to. Sorry, that was the question. Which centroid do I use? So mean shift. Mean shift is a different clustering method. And the cool thing about mean shift is you do not have to know k. You do not have to know how many clusters you're looking for. It's going to estimate those on its own. So the idea is I have for each of my data points, every single one, I put a window around it, and then I compute the mean of the points in the frame. So I basically take all the points that are in this window, right? And then I compute the center if these points would be a cluster. And then I shift this window towards the cluster mean I found. So this is a video that I think very nicely demonstrates what is happening. Here are all my data points, and you can see this is kind of a cluster center. And you have this window, and because there are more points here, right, kind of the weight of the data in that window shifts it with each iteration towards the dense area. So it's a bit the same idea as in k-means, where we had random positions, and those were kind of attracted by the cluster centers. But instead of having k initial positions, now we have to do this for each and every single data point and kind of see where's the next center it gets attracted to. And what you then get are these kind of tracking lines. So this is for each of the data points here. There's a line that connects the way this window shifted. And at some point, it's going to stop. And you can see here, then all the yellow points here were attracted to the same position. And all the blue guys were attracted to the same position. And this is how you find your clusters in mean shift clustering. And now you can see there is no free lunch. I said we don't have to tune k, and that is right. It finds the number of clusters automatically, but there's a sigma up here. What do you think that sigma is? What? Sorry?
The distance of how far it's looking.
The distance of how far it's looking, yes. It's the size of the window. So if it's a very small window, then it only takes a few data points into account and shifts here, and you see you end up with a lot of clusters. If you take a very large window, then you average over a lot of data points, right? You smooth over them, so a lot of them are going to converge to the same position, so you have fewer clusters. So it does not need to know the number of clusters, and also in experience, k-means tends to work well with clusters that are kind of roundish in shape. And mean shift is better with handling arbitrary shapes of clusters, because you can kind of move just towards the center. You also don't have this initialization problem, because you're going from all the different data points. There's no random initialization in mean shift, but you need to set this bandwidth parameter. So instead of choosing k, you need to choose sigma. And it's computationally expensive, because for each and every data point, right, you have to see where it ends up. And this is just a cool application I found, where they did a project using mean shift clustering. And what they did was they grouped trajectories of cars and pedestrians, and then looked for outliers. So this is the input video. It's a highway, and you see this guy here is kind of suicidal and runs across a highway. And then these are the trajectories of the different objects. And they used mean shift to cluster those trajectories into groups. And then you can see you get two clusters here for the two lanes. And then they basically looked which of the trajectories do not fit in with the main clusters. And those were the outliers. This is how you can detect in a surveillance camera a pedestrian crossing the highway. Yeah. So I linked the, I think, not sure, no, that is a blog entry. That is a good introduction to mean shift. And if you Google the first author, they have a paper online if you want to know about, if you want to know more about how this worked. Okay, mean shift clustering. We're going to do a bit of hierarchical clustering because it's the one that is best to visualize. It's kind of the analogy to the decision tree. So in hierarchical clustering, you have your points here, and you start with each single point basically being its own cluster. So I'm, again, not setting the number of clusters beforehand, but I say each point is its own cluster. And then I start and look, in this case, which points are closest to each other from all the different point pairs. So here the yellow and the blue guy were close to each other, so I group them, and I end up with this cluster. And now I look, and maybe these two guys are closest to each other now, so I group those, go further, and now you see I have the first case where I already have a cluster, and this point is closest to this cluster than anybody else. So I'm going to group that now, and this is how you go on. And so what you end up with always is you start with every point being its own cluster, and you end up with all the points in one cluster. Now that doesn't seem very useful. But what you can do now is you can threshold here. You can look at this dendrogram and threshold it. And this can give you your clusters then. So if I put the line here, that would mean the yellow and the blue guy are in one cluster, the green and the red guy are in one cluster, these three are in one cluster, and this guy is alone. And you can shift through this. So you would once compute this tree, and then it's reasonably fast, and you can shift this up and down. So this is nice for interactive things also, like where you need to show the clusterings and fast, and you can have a user then fairly fast adjust the threshold and say, okay, this clustering looks useful to me. So you don't have a predefined number of clusters, and something you need to care about in this hierarchical clustering is how you compute the similarity between clusters. And you can do single linkage, complete linkage, or average linkage, and others, but these are popular. So single linkage means you look at all the different data points from cluster A and cluster B, and then choose the minimum of those. And complete linkage takes the maximum distance between the two. But this is still the similarity measure. So in the end, I group the two that have the minimal maximum distance. I have an example to make this a bit more clear. So this is single linkage, where I look at the minimum distance between all different data points. So if this is my example, just think about we are already further ahead in the tree, and we already have built those three clusters. So it's about the next step now. And the labels here are real. So these two guys here, between all those clusters, are very close to each other. So in the next step, I would merge these two clusters here. That is single linkage. In complete linkage, I look at the maximum distance between all the points in the clusters. So for these points, maybe the maximum distance would be from this guy to this guy. And for these two clusters, maybe here, somewhere in the diagonal. And then I think I used that one. So I actually verified that, but this is still shorter than this. You see how this works? So I take the maximum distance between the points in the two clusters, and then choose the grouping where this maximum is the smallest. So then why do people bother with this? Single linkage, where you just look at the minimum distance. I think this is the most intuitive if you talk about this type of clustering. That has a tendency to form long chains. What that means is going to have one cluster and always going to add one more data point to it, the one that is closest. That happens a lot. Whereas complete linkage does not have this problem, but it's more sensitive to outliers. And this is why people then also try to just build the average of the distances to compromise between the two. I'm not going to do the applet here, but these are two dendrograms of the same data points here. And this has been clustered with single linkage and this with complete. Can you see that this is more balanced? So here you have these chains. Here are the staircases going up, right? Always adding one more, adding one more, adding one more. Whereas here, those dendrograms look more balanced. Like first, there are 2 data points merged, and then it builds up. But this is an example how this, this complete linkage can fail if you have outliers. So you have your data points here, and these are actually shifted a bit. So first, these 2 are nearest to each other, right? So I cluster those. And then this guy is closer. The maximum distance here between those 2 guys is smaller than between this guy. Is that true? And this? The actual question is further on, like the maximum distance. So you would have wanted these 4 data points to end up in the same cluster, right? If I would just give you those 5 points and I would say cluster them, most people would say these 4 belong together and this one is on its own. But if you use complete linkage, because this distance here is smaller than this maximum distance here, you're going to end up with this clustering. So this is a very constructed example, but it shows this outlier sensitivity, that you can end up with this clustering. A nice thing that you can do with hierarchical clustering, it's easy to introduce constraints. And there's this Swiss roll problem. A Swiss roll is actually a cake that is rolled up. And it's very tasty and nice. And it's a famous problem in clustering communities. Because what happens if you just cluster this is you would like your clusters to be along this manifold, right, along the spiral. But what you see, what happens is it jumps across here, because these are still very close together, although there is a gap in the structure here. So what you can do in hierarchical clustering is you can have this additional constraint that says you're only allowed to merge 2 clusters if they're adjacent to each other, which in this case could mean if there is a distance of points you can hop along to go from one cluster to the next, for example. And if you do this, then you can actually solve this Swiss roll problem, right? And you see this is nicely behaved here and clustering the points along the spiral. This is an application in biology where they use hierarchical clustering. It's this tree of life, where they go with all the different genomes, I think, or proteins. What is the tree of life based on, do you know? Phenotypes? Yeah, it's like animals and plants, and you like cluster those, and you try, you hope that basically the animals that are related to each other are close to each other in this tree.
I mean, how do they compute distance?
Yeah, like what's the, on the genome? Yeah. I'm actually going to close here. I wanted to talk a bit more about evaluation and stability and RAND index. I think we're going to do that next time, or maybe I'm even going to skip it. Yeah, I'm going to make that decision later, but I think this is the main information about the clustering that you need. Other questions? So we said k-means, mean shift, hierarchical clustering. Hierarchical clustering, nice for interactive visualization, gaining insight. Mean shift, computationally expensive, but well-behaved for irregular cluster shapes, and you don't have to know the number of clusters in advance. K-mean, fast, lots of implementations out there. You need to know K in advance and do multiple runs. That was the short summary for today. Okay, then have fun. And don't forget about the IICS seminar tomorrow if you have time.